Hi everybody, this is Mr. Nolan, and what I want to talk with you about today is what happens when soda fizzes. This is our central question of the unit, so let's go ahead and make sure that we understand this. So the goals of this particular screencast are that we've got three big ones. One of them is to be able to identify what a scale and BTB say when soda fizzes. So here's our scales, what our digital scales looked like. They recorded our mass all the way down to 1/100th of a gram, very precise. And we also had bromothymol blue. And bromothymol blue, if you don't recall, here's a handy little photograph and color chart just to remind you. The bromothymol blue starts as green, and that's neutral. So, for instance, pure water would be neutral. And yellow means that it has gone a little bit acidic. And then blue means that it has gone a little bit basic. And the pH scale, the lower the scale goes, the more acidic. And the higher the scale goes, the more basic. It's a little bit backwards than what you would expect. So this is one goal, is just to be able to identify what does a scale and the BTB say soda does when it fizzes. You have to remember those observations. The next goal is to be able to explain the observations about mass and pH at the nanoscopic level. In other words, why do the mass and pH change by using atoms and molecules as a reference? What about the atoms and molecules? What are they doing that causes the BTB and scale to give us results? And then lastly, related to this middle one, we need to be able to use a chemical reaction to explain what happens when soda water fizzes. We're going to use chemical reactions here. So if you don't quite recall our setup, this is it. We have a box here, and we took some soda water and we set it next to some neutral BTB that was green, and we placed our box over it, and then we walked away for about 20 minutes. So that was what we did. And so what we want to be able to do is to remember what was it that we observed when our soda water was fizzing, and this, we can see this GIF is fizzing vigorously. What is it that we observe? And look, it's a Coke ad in Spanish, apparently. So the scale. Do you remember what the scale told us as our soda sat here fizzing for a few minutes? What did the scale say the mass did before and after? So do you remember that? If you don't, let me remind you. What happened was the scale reported that the mass was less after the soda sat for 20 minutes. It actually decreased. It went down. The soda lost mass. That seems like a very important observation. It only lost a tiny bit, but it lost mass. And so that's an important observation, a macroscopic observation that the scale gives us. But what about the BTB? What did the BTB do? We set the BTB next to the soda. It started as green. Do you remember what it did? Well, that BTB actually turned yellow. It went from green to yellow. And if you were to report what the BTB did, you wouldn't just tell me it changed color. That doesn't really mean very much. You have to say it turned from green to yellow. You have to report what did it start at, what did it end at. That means that it must have gone from neutral to acidic. If it went from green to yellow, that means it was neutral and it went to acidic. So these are our macroscopic observations. This is what we saw with our eyes on the macroscopic scale. But we need to be able to talk about, to show how to model soda fizzing. So you might know all this stuff, but if you can't model it, then it doesn't do you very much good. So let's kind of think about, how are we supposed to model this? How do we do this? But before we actually try to model this, I do need to remind you of something that you might have forgotten. What kinds of things can turn BTB yellow besides simply saying acid? Well, we actually did a lab where we observed what special certain circumstances would turn BTB, would make it change color. So we know that BTB turned yellow, but why? Well, I want to show you this quick video. We did this in class. I have to credit Andrew Gatt here for posting this. This is a nice quick little video. But this is what happens when you blow into BTB. So we observe here that as he blows into this BTB with his breath, it starts at blue, which means it must be basic. Look at that. Look at that. It changes up through neutral. So he's stopped and it's turned neutral. And as he continues to blow with his breath, it turns more and more yellow. So we see this whole transition all the way from blue through green through yellow. So we can actually see that whole transition take place. So what does this say about BTB and breath? Well, you know that your breath is made out of carbon dioxide. The carbon dioxide turned the BTB yellow. We should remember that. And it's also what we observe happened to the BTB when we set it next to the soda. So that should be a really important clue as to what's going on in the soda. And so let's kind of start sketching here and start figuring out, well, how are we supposed to model what is happening? So I'm going to move over to the whiteboard and start writing a little bit. So in order to help us here, what I'm actually going to do, I'm going to move our glass over so we can have some room. And let's go ahead and actually put our dish of BTB here. This is one way that we could model this. So our BTB is over here next to the soda. The soda is, remember, under a box. So we can include that box here. We can even label it box. And we know that the BTB turned yellow. It went from green to yellow. And so I want to ask you, dear viewer, what does that mean happened in the BTB? Good answer. It means that carbon dioxide went into the BTB. So that's one thing that we can start with, is by indicating, look, we know that CO2 went in. That's a fact. It went into the BTB because the BTB went from green to yellow. We know that for sure. So where did that CO2 come from? Well, you know, the soda water was the only other thing inside of that box. So I think it's reasonable to say that the CO2 came out of the soda. So our soda has CO2 coming out of it and into the BTB. Something to note as well, remember, the mass of the soda went down. The mass actually decreased. The mass decreased of the soda. And so it's reasonable to say, well, that means that some of that mass was probably CO2. Right? So some of that mass was actually because we lost CO2. CO2 came out of the soda, and as a result, that soda actually lost mass. But I don't think this is the whole story here. I think that there's a few more things going on. So this is part of our model, but I think that what I want us to be able to do is actually kind of zoom in to the nanoscopic scale and to be able to say, what else can we model? Is this it? Is this the only thing that we can model, or can we actually go into a little bit more detail? I bet we can. So let's go ahead and zoom into the nanoscopic scale and try to explain why we see these observations. Okay, so I've set up a little diagram here so that we can sort of compare what the molecules are doing in the BTB as opposed to the soda. So let's try to set up some chemical reactions here. So if you remember what a chemical reaction is, it's when the molecules that you start with rearrange in order to make molecules that you end with. That's the whole idea behind a chemical reaction. There's lots of ways to do this. Now, we're just going to start with what we know. So in the BTB, what we know is that CO2 went into the BTB. So that's actually a reactant. So our CO2 actually went into the BTB. That's a reactant. And the CO2, after it entered the BTB, it created some products, and those were an acid. We know that because the BTB turned yellow. So the carbon dioxide sort of combined with something to turn into acid. And I ask you, dear viewer, what was the only other thing in the Petri dish besides BTB itself? Well, the BTB was dissolved in water. That's what was inside the BTB was water. So really, we're combining our CO2 with water. That's it. We're just combining that with water, and we end up with some kind of acid. That's sort of interesting, but we know it must be true because when you blow into the BTB, it turns yellow. Well, what is that acid? Now, I'm going to show you. That acid is H2CO3, and we call this carbonic acid. So carbonic acid is what's in that soda. It's a very mild acid. Don't worry, it's not very bad for you. And so actually, the carbonic acid is being created inside of the BTB when the CO2 and the H2O combine. This is a chemical reaction. And if we really look carefully at our atoms, we find that we have the same number on the left as we have on the right. There's one carbon there. There's one carbon on the right. There's actually 3 oxygens on the left side. There's 2 right there in the carbon dioxide. There's 1 in the water. and then they show up over here in my O3. And there's my 2 hydrogen atoms, and then those are over here, 2 hydrogen atoms in the carbonic acid. We could draw these structures out, but I'm just kind of trying to show you the basic idea behind the molecular the reaction. So let's think about what's happening inside the soda. So carbon dioxide's coming out of the soda and going into the air, into the petri dish, and it's creating carbonic acid. So all that we know for a fact is that for the soda, we are ending with carbon dioxide. Our soda is actually producing CO2. Right? So these are actually our products. If we're talking about the soda, these are our products. And so that's all we really know for sure. But I'm going to help you out with this one too. If we think about what's in that soda, we already have CO2 and water inside that soda. And so that soda, what's interesting about it is that the soda actually starts with H2CO3 in it. This is a reactant as long as we're talking about the soda. Our H2CO3, our carbonic acid, the same thing that showed up in the BTB, actually breaks down inside the soda during this reaction. Right? During this reaction, it actually breaks down to form CO2 and something else. And that something else has got to be water. Pretty interesting. So here's the takeaway from this sort of table that I just showed you. We know for a fact that BTB we're creating acid inside of the BTB, so that's why I put it on the product side. The only thing that we know is going into it is CO2, and we know water's already there. So if we just use some logic, well, carbon dioxide plus water must give us acid, and this is the acid, right? You just add up all the atoms, there it is. Our soda's a little bit more complicated because all we know about it is that it's producing carbon dioxide. That's really all we know about the soda. But if we think backwards, well, why don't we just assume that that acid is in there, it's breaking down to make carbon dioxide and water as products. So this carbon dioxide is actually the source of the carbon dioxide that goes into our soda water. So what we have here, really, this is a nanoscopic explanation showing how does this work. So let me really quickly kind of sketch that up here. How would you actually model and sketch this? Okay, so here's how I think that this makes sense to us, would make sense. So we know that in the BTB, we're taking our CO2, and that's being combined with water, and that gives us our carbonic acid, H2CO3. So that actually explains what we observed down here. It's going from neutral to acid, and that carbon dioxide is coming in from the soda, okay? But now in the soda, we have a different situation going on. We're actually starting with H2CO3, and this is actually breaking up into CO2 plus H2O. This is actually doing the opposite of this reaction over here to the right. So if we think about these reactions, this makes sense. This is why our soda loses mass, because this carbon dioxide is actually leaving, right? This is mass that's leaving, and mass is showing up in the BTB and also in the air, right? So the air is actually getting heavier as well. So what we've now done here, what we've completed, is that we figured out that we're starting with our H2CO3, our acid in the soda. It's breaking down into carbon dioxide and water. The carbon dioxide takes off, right? It leaves. And so when it leaves, our soda becomes lighter. It loses mass according to our scale. That carbon dioxide shows up inside of our BTB. We've got our carbon dioxide plus the water that's already there gives us that acid. That's why it goes from green to yellow. That indicates that there's an acid. So this is really the model that you should understand, being able to use mass and carbon dioxide and BTB and scales in order to explain what is all going on when soda water fizzes. So to review our goals, hopefully by now you should be able to indicate what do the scale and BTB say about the soda, what do those observations say about at the nanoscopic level, and you should be able to use a chemical reaction to explain what happens when soda water fizzes. So I hope this has been illuminating and this helps you understand how to model what happens when soda fizzes.